The next thing we're going to look at is another example of using rotational Newton's second law. And this time we're going to end up dealing with a pulley that isn't magic anymore, at least less magic. That we're still going to neglect internal internal friction at the pin, which is the reason why if you spin one, it will eventually stop. But if you play with one of the pulleys that we had in the lab and you just spun it, it will spin for a while if you have very little torque, very little tension in the pin. But what we want to think about though with using a pulley now is if we have a piece of wire that's coming in one side and coming down the other. In order to understand part of what happens, you can end up thinking about it just with one of them coming off the side. So if you think about, if you've got some string on a spool, and you end up taking the edge of the spool, if you particularly mount this inside something so it's free to rotate if it wants to. So if you pinched it, then you've got friction between your fingers, so it probably won't rotate. But if you have, like a nail or something that will go through it that you mount on here, if you pull the string, then the spool will spin. And this same idea is going to happen whenever you end up having a cord that goes along the side of a pulley. So the pulley itself will end up spinning. You might have noticed this, you might not, because you may well not have been looking to see this. But whenever you had in the lab where we did the Atwood's machine, that whenever you had the two weights on it and they were different, so then it started to move. In that situation, if you did pay attention to what was happening up at the pulley was spinning whenever you ended up having the motion of that. Again, you may not have paid attention to it, but it did happen. So we want to end up talking about how we can end up describing that motion, and a way to look at it will give a specific example, and this one again is in your notes. We'll end up setting up a solid cylinder pulley, and the fact that solid cylinder will make a difference. We'll come back, we'll see in a minute. So a solid cylindrical pulley will have a mass over here and then have a mass hanging down from it, the mass on a frictionless table. So we're going to ignore issues with friction because there's going to be enough math involved in this without dealing with the math with friction too. And we'll look to compute what the acceleration of the 6 kilogram mass is. And the pulley has a mass of 0.5 kilogram, which we will, so in terms of how we address it, we'll look more specifically at what's happening around the pulley. So around the pulley, we'll end up having a tension from the horizontal cord, we'll have a tension from the vertical cord. And the pulley has a radius, because it's circular in that direction, and it's spinning around the center of the pulley. So the radius is going to end up being the magnitude of the lever arm. So you take so the torques from both of the two cords attached will end up being your radius times the amount of tension times the sine of the angle. And we mentioned before in class, and again you can check it again with like a spool of thread, you can see that where it will be attached will be perpendicular to the line to the center of the spool. So if you end up getting those two torques. However, the two torques are opposed to each other, and so in terms of doing this, I will encourage you to end up, and I will try to make this work with using my left hand, because again the camera reverses stuff. So you'd end up having your torque from tension 2, the one that's hanging down, will end up having a radius which should be going to the right, and then it will end up curling toward down. So if you do right curl down, you end up getting the direction that would end up going into the screen. And then torque 1, that lever arm will be going up to where the tension is attached. So it will be up crossed to the left. So that will end up going out of the screen. So they're in opposite directions. And moreover, in terms of thinking about what will happen, if we have those attached to where they are, it will spin in such a way that the one that's hanging down will fall. So it will end up spinning in the plane of the of your screen. It will end up rotating clockwise, which corresponds to the direction of the second torque. So it will be the second torque minus the first torque, then, will equal the moment of inertia times the angular acceleration. The moment of inertia, that's where it becomes important that it's a solid cylinder. So from there you go back to your moment of inertia table, and your moment of inertia table for a solid cylinder around the center, it's 1/2 the mass of the object times the square of the radius. So that's where I get 1/2 the mass of the pulley times the square of the radius, then times your angular acceleration. Now, in order to relate your angular acceleration to the linear acceleration, remember when we define tangential acceleration, that's how fast an object on the surface is moving. And when it rolls without slip, which again is basically always going to be the case with a pulley, it'll roll without slip. So then the tangential acceleration of the chord on the surface will be equal to the radius times the angular acceleration. So we end up putting that into the equation. We solve that for angular acceleration, and then plug that in. The last thing is the acceleration of the chord is going to be the same as the acceleration of both of the masses that are attached to the chord. So in that situation, then, the acceleration, of course, of the one that's horizontal will end up moving toward the pulley. The one that's hanging down will move down. So all of those accelerations, the magnitudes are the same. And so we can calculate then that my net torque, which is my radius times the second tension, minus the radius times the first one, again minus because they're in opposite torque senses, will equal your moment of inertia, 1/2 the mass of the pulley times the square of the radius of the pulley, times the acceleration divided by the radius of the pulley. You do a little bit of algebra there, and that ends up giving you then the difference between the tensions is going to be 1/2 the mass of the pulley times the acceleration. Now this is different from what we did before. So this is now no longer a magic pulley. And what made it a magic pulley was that the mass of the pulley was 0, which of course there's no such thing. It's the reason I call it a magic pulley. So with a more realistic pulley, the tensions will not match on both sides of it. And so that's how you end up getting what the difference between those two tensions are. The rest of the problem we end up putting together more or less like what we've done before when we had an acceleration of things along with a magic pulley. So you go through, you do Newton's second law in terms of the first mass, the mass on the table. The free body diagram, we have normal force going up, we have the weight going down, we have the tension going to the right, which is causing the acceleration of the block. And the normal force and the weight will cancel each other out because it's on a horizontal surface. And there's no friction force, so there's no force going in the opposite direction from the tension. So it will simply be the tension will equal the mass times the acceleration. And similarly for mass 2, we got the tension going up, we got the weight going down, the weight is winning. So, and the acceleration is in that direction. So if we choose the up direction to be positive, which is the way I'd write it on there, then it will be the tension minus the weight equals the mass of the second one times the negative of the acceleration, because the acceleration is going in the negative sense. So you solve that, Then you do some algebra. You combine those equations together, solve for both of your tensions. Plug that into your tension 2 minus tension 1 is half the mass times the acceleration. Again, the 1/2 comes from the 1/2 mr squared. So if it was a solid, if it was a something more like a heavy wheel with light spokes, if we neglect the mass of the spokes inside, then it would be almost the mass, basically, of the rim times r squared, because all of the mass would be on the outside. So again, the 1/2 is because it's a solid cylinder. But then you go through and you solve, and I ended up computing there that your acceleration then comes out as 7.12 meters per second squared, which is a little bit different, a little bit less than what the acceleration would be if I had a magic pulley. And in order to understand why it should be less, notice that in terms of thinking of it in energy terms, then the gravitational potential energy from the falling mass 2 has to provide kinetic energy now to mass 2, to mass 1, and to the pulley, which we neglected that contribution. So because it's spread out over more of them, the speed increases less, and so your acceleration is less. All right, then